Hello, my name is Scott Harlow. I'm at the Office of Space and Defense Power Systems. That's NE75 here in Germantown, Maryland. I'm going to be giving you a little presentation about what our group does and the kinds of proposals that we're interested in receiving. So Space and Defense Power Systems program goals are to design, develop, build, and deliver radioisotope power systems for both space exploration and national security needs. We support research and development in the design of fission power systems for space exploration and national security needs as well. The benefits of this technology are to enable customer missions in locations that cannot traditionally be fueled by solar power or batteries. Typically, these are areas where those systems do not work. We can use radioisotope power systems. We directly support NASA missions to explore the Moon, Mars, and the outer planets and beyond. The key research goals that we have are the development of materials for use in extreme environments, and these are required for the extreme environments of space applications. So we provide nuclear power sources for the space science and exploration missions and national security applications, for which solar and other power sources are not practical. We maintain the capability to produce and deliver plutonium-238 fueled radioisotope power systems at our national labs. And our office reports to the Deputy Assistant Secretary for Nuclear Reactor Technologies. So that's NE7. We work with NASA to provide radioisotope power systems for use in space, and we work for NASA to maintain the ongoing capabilities at our national labs by awarding contracts to our supporters, as well as for the design, fabrication, and delivery of space power systems. I have a slide up right now that shows you all the missions that we have supported over the years. It wasn't long ago we were celebrating our 50th anniversary of helping the United States explore outer space. So some of the things that we have been involved in that were more popular were the Apollo program, Pioneer, Voyager, Galileo, Ulysses, and Cassini. Cassini is still up there doing its thing, even though it was launched in 1997. On the way to Pluto right now is the Pluto New Horizons mission. Back when my daughter was in 4th grade, I went to her elementary school and gave a presentation about the Pluto mission. And this fall she's starting college. So we're still on the way. We'll be there sometime around July of 2015. But you can see our understanding of Pluto is not that great right now. Even using our best telescope that we have available, the Hubble telescope, you can see it's just a little pixelated blur. By this time next year, we're going to have some really interesting information about Pluto. Another one of our recent successes, you've probably read a lot about it, is the Mars Science Laboratory. We provided the MMR-TG, multi-mission radioisotope thermal electric generator that was powering that system. And it's been up there for 2 years, and we're likely going to be extending that mission, assuming funding is available from NASA, which I'm assuming it will be. It's a very important mission. So this is just a little bit more information about the MMR-TG. It's 110 watts, fueled with plutonium oxide, and it was launched in 2011 on the Mars Science Laboratory, also known as the Curiosity rover. The nuclear thermal propulsion is a new area that we're exploring with our NASA partners, and we're going to try to get a reactor system onto that as well. That's in the early design stages. So here are a few of the key components of the plutonium-238 fueled general purpose heat source. You will see that there is a fueled clad in the middle. It's near the top there. It's iridium. It's a very strong metal. It maintains its ductility during pretty much any condition that we can postulate for it. And then we have several layers of cladding that are surrounding it in case there is some kind of launch accident or if there's a re-entry accident. The idea is that the plutonium-238 would stay encapsulated and not get out into the atmosphere and adversely affect the environment. So we have the graphite heat source protecting the plutonium-238 fuel. And then on the bottom right, you have the converter, which converts the heat of the plutonium-238 into electricity. And then you have the radiators that reject that heat into space. So one of the things that we're trying to do is to make sure that the technology development that we stay on path to is to enhance the safety performance and contain the nuclear material in case of accident conditions. So there's a lot of science that has gone into the material selection. We use a ceramic fuel form. The plutonium oxide will not readily vaporize, so it stays in large particles that are not respirable. And then we have the aeroshells and other structural components. We're always trying to lower system mass, so we're always trying to find things that weigh less. Sending things into space is expensive, so we try to keep the weights down. And NASA always has that as a goal for us. Keep the systems smaller, just so they can have more of their cargo capacity for the science that they really want to do on the mission. And we're always working to enhance our worker safety, produce our fuels in a defect-free manner, so we don't have any material waste. And that's pretty much the story. One of the things that we're looking to do right now, and this is one of the things that we'd like to receive proposals on, are designs of small reactor systems in the 2 kilowatt electric to 40 kilowatt electric range. And these designs, we would like them to be able to benefit both NASA and the national security user environments. They're intended that they would probably be something that would be in space. And we're trying for a simplistic design that's easy to manufacture, and like I was saying earlier, trying to minimize the system mass. So the innovative design concepts that leverage the existing fuel expertise with focus on high reliability power conversion and reactor operations. So the proposals we would like to see are for conceptual designs for reactors and fuels that cover the range of power outputs from 2 kilowatts electric to 40 kilowatts electric, suitable for nuclear space applications. As I said earlier, we'd like to keep the design simple to help avoid a costly development program while assuring the ease of operation and reliability. Because once you put a reactor in space, you're not going to be there to maintain it. You're going to have something that's reliable on its own. So the second item that we're interested in receiving proposals on, most of our power systems to date have been based on plutonium-238, but we understand there is a push for others to build radioisotope power systems that run on MS-RC-2 So our safety basis is entirely done for plutonium-238 at this point. So we would need help with understanding how an MS-RC-2 fueled RTG would perform in an accident scenario. So when we're doing our safety analysis work, we would have a methodology to determine how to do that nuclear risk assessment for a different material. So that's pretty much what I'm here to ask you to propose. If there's any questions, please let me know.
Scott will be here for the next few minutes to answer any questions. Please submit them to your question box if you have any. Start with the first question, Scott. Can I collaborate with NASA? Will a NASA co-PI be able to get funding from any UP?
I don't believe that any UP system is set up to get co-funding from NASA, but I guess we could look into that and we could get back to you later.
We can follow up with any details if we need to by email. The next question is compact fission power considered in the solicitation? And what is the expected lifetime?
Compact fission power is considered in this solicitation. The lifetime that we would like to see, when I was involved in the fission surface power system development a few years back, we were looking at a 5-year reactor lifetime for that. I would think probably in that same range.
Are there any potential next that would be good for this area?
Yes, we have support at both Randall and Idaho National Lab, and for materials work we have support at Oak Ridge National Lab. For safety support we have Sandia National Lab.
To submit a full proposal in this area. How many proposals could possibly be funded this year? What is driving 2 to 3 kilowatt at the lower end of the power system range? Would a lower power reactor system also be of interest?
Lower than 2 to 3 kilowatts? We find that that's about where fission surface power, or fission power starts to make sense, right around the 2 to 3 kilowatts. But I think you could probably propose something smaller still. I just don't know that it's all that efficient. And as long as you're building a reactor, you might as well get some higher power out.
Should the conceptual design be tested?
Testing gets to be rather difficult, but we could do something that would be an electrically heated conceptual design, wherein the fission part would be replaced with an electric